Long-term exposure to cortisol has a lot of damaging effects throughout the body, but we're going to focus on how it changes the brain. Prolonged exposure to cortisol can decrease the function of your prefrontal cortex, the area of your brain in charge of decision-making, concentration, memory, and regulating your social behavior. And a lot of folks really felt this effects in the early months of the coronavirus pandemic, a period of prolonged stress for all of us. People talked about coronavirus brain fog, how the stress of living through a threatening event like the pandemic was making it harder for them to concentrate at work and at school. You probably felt it. When we studied the limbic system, layer 2 of the brain, I mentioned that periods of prolonged stress can cause the reward network to produce less dopamine. Here's what I said. Chronic, ongoing stress or pain can dull activity in the reward network, and this accounts for one of depression's most classic clinical diagnostic features, which is anhedonia, the inability to feel pleasure. Prolonged cortisol exposure has other effects on the limbic system as well. It increases the connections between neurons in the amygdala and results in more activity there. If the stress is prolonged enough, the amygdala can actually grow in size. Now, this might make sense from an evolutionary point of view. If you're a rat born under really trying times and you're destined to live a difficult life full of competing for limited resources, perhaps you want this giant amygdala to make you extra attuned to threat and danger. It might help you survive, but life won't be pleasant. In humans, an amygdala that's been boosted in size and strength by prolonged exposure to stress hormones can result in us seeing the world as a more threatening place. In laboratory studies, scientists have shown participants' faces with a neutral expression, like this one. Folks with an enlarged and overactive amygdala were much more likely to rate this neutral face as angry and aggressive. Folks with neurotypical amygdalas tended to rate these neutral faces as neutral or even positive. Something we've been saying since the beginning of the course is that your brain creates your reality. And here we have another example. An overactive amygdala can cause you to live in a scarier world as you interpret neutral stimuli in a more threatening manner. At the same time that it's increasing the size and power of the amygdala, prolonged exposure to cortisol can shrink the hippocampus. To understand the implications of this effect, let's review what the hippocampus does. Do you remember the main functions of the hippocampus? Give yourself a moment to try and recall. If you did remember what the hippocampus does, you actually have your hippocampus to thank. It's the part of the limbic system involved in the storage, retrieval, and processing of memory. It's this seahorse-shaped structure that connects to the amygdala and wraps around the limbic system, and it has a couple of important functions. First of all, it's the only place in the adult brain where new neurons are born. And prolonged stress seems to damage this process of neurogenesis. The hippocampus is also, of course, the processing center for new memories. A very common misconception is that memories themselves are stored within the hippocampus. This isn't the case. Memories are stored all throughout the cortex. The hippocampus functions as a memory processing center. We compared it to a loading dock, where each day's memories are sorted and processed, and the important stuff gets sent off to long-term storage. So it should come as no surprise that the problematic effects of prolonged stress on the hippocampus can interrupt learning and memory processes. So these are both functions of the hippocampus we've previously discussed. To help you completely appreciate how problematic the effects of prolonged cortisol exposure can be, I have to introduce one more new function of the hippocampus that I haven't told you about before. One of the hippocampus's functions is that it actually helps the brain to turn off the hormonal stress response. Let's talk about how that works. So I'm using this seahorse to represent the hippocampus. It turns out that the hippocampus is covered in, so here's my little cortisol receptor, and I'm showing that the hippocampus is covered in cortisol receptors. So it's very sensitive to the presence of this stress hormone. When cortisol levels are high, the hippocampus tells the brainstem to shut off the hormonal stress response. So the hippocampus sort of works as the brakes on this hormonal stress response system. When it detects high levels of cortisol, it sends a message to the brainstem to shut down cortisol production. This is part of what keeps us from staying at an elevated cortisol state for too long too often. So here's a question for you. What part of the brainstem do you think the hippocampus is sending its message to? What area of the brainstem regulates hormonal function? Do you have a guess? It's our old friend, the hypothalamus, in charge of maintaining homeostasis by monitoring the body at all times and in charge of the entire hormonal system through its connections to the pituitary gland. Now, since I gave you an adorable cartoon seahorse for the hippocampus, I really didn't want to leave you with this less exciting drawing for the hypothalamus, so I found an adorable hypothalamus cartoon. So here we've got the hypothalamus with the pituitary gland hanging off of it, and he's working as a little scientist down in the brainstem, constantly monitoring all of the body's needs to make sure that you're in homeostasis at all times. So when the hippocampus detects high cortisol levels, it sends a message to the hypothalamus, prompting it to turn off that hormonal stress response. I've said before that the nervous system is really good at listening to itself, particularly when it comes to regulating homeostasis. The body's full of feedback loops, and this is one of them, the natural system of communication between the hippocampus and the hypothalamus to control the hormonal stress response. But what happens when the hippocampus itself is damaged by too much cortisol exposure for too long? It's a grim scene. Since part of the hippocampus's function is to help the body regulate cortisol levels, what happens when the hippocampus itself is damaged and shrinks because of exposure to prolonged levels of cortisol? It's not a good scene. Under prolonged stress, high levels of cortisol secretion damage hippocampal neurons. Now, this weakened hippocampus with less neurons is less able to send those signals that shut down the hormonal stress response. This creates a vicious cycle where periods of prolonged stress actually harm the brain's ability to manage stress itself. So it's this pattern of brain-related changes due to prolonged stress that make trauma recovery so difficult. An overactive amygdala seeing danger when it isn't there, and a weakened hippocampus unable to regulate the hormonal stress response. There's also really good evidence to suggest that this biology is what creates the condition known as post-traumatic stress disorder. PTSD is a mental health condition characterized by constant high levels of physiological arousal, feeling keyed up all the time. And it's triggered by either witnessing or being part of a traumatic event. Symptoms of PTSD include flashbacks, nightmares, troubling recurring memories about the event that are intrusive and make it hard to get through your day, and anxiety, sometimes severe. PTSD is usually diagnosed when these symptoms have persisted for months or years after the traumatic event has taken place. Cortisol's influence on the memory system is part of the biology that underlies post-traumatic stress disorder. Scientists have done 2 large-scale studies of the brains of people who've been through traumatic experiences. One was a study of combat veterans, and they found that an extraordinarily high proportion of those coming back from active duty combat showed both of these 2 brain changes, an increased strengthened amygdala and a decreased weakened hippocampus. Neuroscientists testified about these brain-related changes in Congress in the 90s, and that scientific testimony was crucial to getting more funding funneled into PTSD recovery for veterans. Most of the time, the brain recovers from these stress-based changes on its own if you are able to provide yourself with sufficient time to rest and heal. But for folks with PTSD, the road to recovery is harder, and they often need professional help. So, if this lecture about how the long-term effects of stress can damage your brain has you feeling stressed out, you're not alone. This topic's stressful to me too.
Thankfully, our study of the nervous system also reveals a lot about how we can reduce the amount of stress we experience, cope with the stress we do feel, and protect ourselves from the long term effects of stress. Over the next couple weeks, we'll review what we've already learned about dealing with stress and add to our knowledge.